To construct a nose cone, we seek the optimal dimension and the best material for it. But directly optimizing both continuous geometric parameters and discrete material choice is difficult. Due to limit time, we only discuss which good candidate material are selected mainly based on their thermal performance, which is widely known as Thermal Protection System (TPS), or a more brand new technology, Integrated Thermal Protection System (ITPS). In combination with a material database, its procedure allows a graphical comparison and selection of candidate material. First, list some prescription. Function: block aerodynamics heat to protect the nose cone. Constraint: withstanding 1600 degrees Celsius. Objective: to save energy, we prefer to minimize the mass. Free variables: the thickness, structure, and processing methods. TPS technology has been developed, such as ablative TPS used mainly on the capsules by lifting the hot shot layers gas away from the heat shell afterward. The powdery layers come from blowing of gaseous reaction products from the heat shell material itself and provides protection against all forms of heat flux. The typical corrugated core assembly panel ITPS structure consists of three parts: top face sheet TFS, which is equivalent to external surface; bottom face sheet BFS, the internal surface; and width is the structure between them, which we don't discuss in this time. So, calculating how much heat TFS can solve is equivalent to calculating the maximum BFS temperature, which we want to maintain within about 25 degrees Celsius. We developed a finite element model using ANSYS. The geometric parameters are like this. To simplify calculation, we use NASA past case as constant. Radiation is also modeled on the TFS with an emissivity of 0.8 from Dr. Williams' Thermal Protection Material 1992. Now we can assume this is one-dimension homogeneous heat transfer behavior. During search for materials suitable for the TFS, the following requirements were imposed: the mean acceptable max service temperature higher than 1800 Kelvin, Young modulus higher than 50 GPa, fracture tautness higher than 15 MPa times m power of 0.5, density lower than 6000 kg per m3. The only purpose of the requirement on Young modulus, fracture tautness, and density was to avoid the materials that were good from thermal property but extremely poor from a mechanical point of view. After calculation, only 5 materials in the CES selector satisfy our requirement. Carbon-carbon composite is also added to the figure taught. They do not satisfy the fracture tautness requirement. However, this material is currently used as part of the TPS of the Space Shuttle Orbiter. Carbon-carbon composite has a very high maximum service temperature while still having a reasonable high Young modulus. Their major drawbacks is their fracture tautness, and considering that this was a contributing factor to the Space Shuttle Columbia disaster. This is why we choose this topic. This is a thermomechanical optimization problem. Let us skip the analysis and show you the result. In the end, we have chosen the aluminosilicate 720 composite for TPS. Using aluminosilicate 720 composite for the TFS compared with Inconel 718 in that we can save about 50% max. This significant improvement is because Nestle 720 composite have about 3 times lower density compared with Inconel 718. It also reduced the thermal mismatch between the TFS and the web, which alleviates bugging and make it possible to have much lower thicknesses for these two sections.